everything we've done has been what we call collinear vectors. Collinear just means one dimension. A one dimension, it's either north and north, or north and south, or maybe it's east and west, or maybe it's east and east, or maybe it's 37 degrees north of west and 37 degrees north of west. But we haven't, at least until this point, dealt with a north and an east in the same problem, or a south and a west in the same problem. Today we're going to start dealing with what we call non-collinear vectors, vectors that are in two different dimensions. We've got an east and a north, as opposed to an east and a west. Does that make sense? In order to do that, we have to learn to analyze what we call vector components, parts of vectors that are in certain dimensions, x dimension or y dimension. So we're going to work through that today, identifying different components of vectors, and then depending upon time, we may get to the actual analysis of vector addition, of vector calculations. Hey, before I go over this page, let me just show you one little thing kind of off to the side here. I'm going to draw a little coordinate system here. It's what we call our XY coordinate system. Can you tell me which axis here, actually, let's do this in different colors here. Let's do blue and red here. Can you tell me which one, gentlemen? Can you tell me which one here is x-axis and which one is y-axis? We should know this from math class, right? Okay, which one is x-axis, Marshall, and which one is y-axis? Yes. Good. The blue one is x-axis and the red one is y-axis. You got to remember that, right? You got to remember that. Now, when we talk about the x component of a vector, we're going to talk about the part of a vector, how much of the vector is on the x-axis. Now, most of these that you see up on the board here are actually quite straightforward. Okay? If I look at this one, how much of that is on the x-axis and how much is on the y-axis? We don't know any values here, but in the end, we would say that all of that vector is x-axis, right? How much of this one is on the x-axis? All of it. How much of this one is on the x-axis? All of it. How much of this one's on the x-axis? This one right here? What is it, Jacob? None of it, right? None of this is on the y-axis, none is on the y-axis, none is on the y-axis, and all of this is on the y-axis. Got it? Okay, let's take a look at these ones. How much of this one is on the x-axis? All of it. How much is on the y-axis? None of it. X-axis? None. How much is on the y-axis? All of it. X-axis? All of it. Y-axis? None. Okay, how about this one? X-axis? Okay, all of it? None. On the y-axis is? None. X-axis? None. Y-axis? All of it? How about that one? Don't panic about writing these down necessarily, by the way, guys. We're working through this, but there's more to this, and this is kind of just the very, very intro to it. So if you're writing down a couple of them, that's fine. If not, that's fine too. How much of that is on the x-axis? Some of it. How much of it? Well, we don't have any numbers, so it's pretty difficult to say how much of it is on the x-axis, but some of it, right? Some of it is going to the left, right? How much is on the y-axis? Some of it. Some of it is going left, and some of it is going down. So these ones are nice and easy, right? All of these, except for this one, are easy. They're all either x-axis or they're y-axis. But when we have this one that's at this crazy funny angle, we have some of it on the x-axis and some of it on the y-axis. Good? Make sense? Okay. Let's take a look at example number 13 and identify how much is on an x-axis and how much is on a y-axis. All right, let's take a look at this first one here. We got 10 meters, and it's 10 meters to the right. How much of this is x-axis? All of it, right? So we're going to say x is equal to 10 meters, and we're going to say y is equal to, well, if all of it was x, then how much of it's y? 0. How about this next one? 7 meters is going up. How much of it's x? 0 meters, right? Because it's all y-axis. That means that we're going to say the y-axis is 7.0 meters. Good? These ones are easy, right? How would you find how much of this is x-axis, do you think? We're not going to actually worry about calculating this necessarily at this moment, but just the steps in getting to the point where we would calculate how much is x-axis and how much is y-axis. If we look at this, it's going up and to the right. How much of it's up? Well, we would say this much of it is up, right? So this would be the y component of that. Now, what that value is, I don't know what the value of that is. We could find it. I'll tell you in a few minutes how to find it, but just know that that is the y component. Whatever that number is how much of that is on the y-axis. This would be our x component right here, our x-axis. Does that make sense? Right now, let's just identify what is x, what is y, and then we'll go back and do all of them and determine how much of it, the actual values of it. What about this next one? Marshall's going to come up and he's going to label with blue for us the x component. He's not going to calculate the value, but he's going to label the x component of that 7 meters, and he's going to label the y component with red. See, guys, doesn't that look fun? Is he right? Hold on, whoa. Please. No, just hold on for a second. Just take a step back. You don't have to sit down yet, though. Just take a step back for a second. Okay? Is he right with this one? Yeah, almost. Almost. He's missing something on this one that he did, though. He's real close. What's he missing on this? What's he missing, Aiden? Yeah, he's missing the direction. So do you want to show us the direction of the x component on that 7 meters? And the direction of the y component? Okay, there's the x component. Good. Now the y component? Good. Is he right on that? Absolutely. Good. So the x component is to the left, and the y component is up. If we would actually calculate the value of the x component, which we will soon, it would be actually a negative value, right? Because it's to the left. The y component of this would be a positive value because it's up. So we can have a negative and a positive value for x and y components in the same problem. All right, you're up here. You want to do the next one too? Don't forget your directions, though. Oh, you can fix that. You know how you fix that? There you go. Now do the y component. Sorry, the x component. Is he right, by the way, for that? Yeah, absolutely yes. He's got, just step aside now. Thank you. He's got an x component labeled to the left, is that correct? Yep. He's got a y component labeled down, is that correct? Yep. Absolutely, good. Don't forget those arrows, right? He's drawing a little triangle around the angle, and then he's drawing little arrow tips to show the direction of those components. One more, Marshall. Might as well finish it off since you're up here. So he's drawing the y component downwards, is that correct? Absolutely. Hold on for a sec, Marshall. He's correct here, but why isn't he drawing the y component down here? Like, why didn't he do it over here? Because the angle's over here, right? Draw the y component where the angle is, not some other crazy place, right? So, good. You're good? Got the x component? Good. Is he right? Absolutely. Now, how do we find the values of those components? Anybody want to take a stab at how we might find the values of those? Like how much, like what is that number x right here? What is it? Base? What about base? Yeah, you could say it's the base, but if you're going where I'm thinking you're going with this, it's not quite where we want to go. Yeah, it's trig. It's not 1/2 base times height. We're not finding the area of a triangle or the area of a rectangle. We're not doing Pythagorean theorem or anything like that. We're doing trig. We're doing sine, cosine, tan. You remember that? Math 10, I think it was. Maybe Math 9. If you remember this, sine theta is opposite over hypotenuse. Cos theta is adjacent over hypotenuse. and tan theta is opposite over adjacent. You should probably write this down. You guys usually learn it as SOHCAHTOA. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. Now, what's our opposite, adjacent, and hypotenuse sides? Well, if I draw a triangle, it doesn't have to be a vector diagram triangle, but just any triangle, and I label an angle right here, theta. This has three sides. One of them's opposite, one of them's adjacent, and one of them's hypotenuse. The one that I like to identify first is the hypotenuse. By the way, this only works if it's a right-angled triangle, right? 90 degrees. Why do you think that I like to identify the hypotenuse first? That's the easiest one, right? Why is it the easiest one? Because it's the longest one. Good. So this one right here would be the hypotenuse, the longest side. Now notice the hypotenuse is also touching the angle. Right? It's also touching the angle right here. There's one other side that's touching the angle as well. There's one other side that's adjacent to the angle as well. Which side do you think it would be? Besides the hypotenuse, which side is adjacent to the angle? What is it? Yes. Like this one here. What is it? What do you call it? Yeah, it's the adjacent side. It's the adjacent side that is adjacent to the angle. So is the hypotenuse adjacent to the angle, but we don't call that adjacent because the hypotenuse is the longest side, and it's got its own special name, right? Hypotenuse is adjacent, but it's the longest side. The other side that's adjacent is called the adjacent side. Now, the other side, the one that's not touching the angle at all, the one that's kind of opposite to the angle, we're going to call the opposite side, right? It's the opposite side. So if you've got this angle and maybe the adjacent side, and you want to find the opposite side, you would use theta, adjacent, and opposite, which would be tan theta. If you have, let's say, the angle, and you have the adjacent, and you're looking for the hypotenuse, then you're going to use cosine, because you have theta, adjacent, and hypotenuse. If you've got, let's say, the angle, and you've got opposite and hypotenuse, or you're looking for one of those two variables, opposite or hypotenuse, you're going to use sine. Sine theta is equal to opposite of hypotenuse. So in the end, there's really four variables you're going to be dealing with in any one problem involving trigonometry, three variables. Theta, opposite, adjacent, hypotenuse. You're going to be dealing with three of those four. Look at what you've got and what you're looking for, and identify which trig function matches up best with that. It's kind of like, remember I said those acceleration equations, the way that we think of it carries through all through physics 20 and physics 30, even if we're not necessarily using those equations per se. Okay, it's kind of the same thought process here, right? We look at what we've got. Theta, adjacent, opposite, hypotenuse. They're all valid. They're all valid with this triangle, but you're going to find that one of them is the one that you use depending upon which givens you have. So make sure that you understand which side of a triangle is which. Okay, write down what you got, and then look at which of these three equations matches up best with that. Does that make sense? Okay, let's go back to this. Knowing that the third example here, if you notice, by the way, guys, example number 14 is the exact same thing, except example number 14 asks you to actually find the values. We've already done that for the first two. We're going to do that now for the last four. Okay, so we're really combining example number 13 and example number 14 here. I've got an angle here. This isn't labeled very well, but this is supposed to be 30 degrees right here. So I've got theta, right? I've got theta. And what's this side right here? 10 meters. That's the hypotenuse, right? I'm going to label that, although as time goes by, you're going to get good enough at this that you're not going to need to label it. You're just going to keep in your head that that's the hypotenuse. If I want to find x, which side of the triangle is x? Which side of the triangle is x? Not hypotenuse, right? It's not hypotenuse because we already identified that. That's the longest one, the 10 meters. Jacob, which one is x? Yes, that's the adjacent side. All right, so if I've got hypotenuse and theta, and I'm looking for the adjacent side, which of these trig functions am I going to use? Again, theta, adjacent, and hypotenuse. Which trig function am I going to use? Cosine. So let's say for x, cosine 30 degrees is equal to adjacent over hypotenuse. Does that make sense? Cosine 30 degrees is equal to adjacent over hypotenuse. That means that x is equal to, how do you take the 10 over to the other side? Multiplying. It's equal to 10 cosine 30 degrees. Now, pull out your calculators. I want everybody to do this with me. Don't just watch me. Everybody do it. Do it with me here. The first thing that I want everybody to do, whether you've got this calculator or some other calculator, is a little test to make sure you're in the right mode in your calculator. In math class, as you go on in math, there's going to be a lot of times you need to be in radian mode for angles. In physics class, Ryan, have you taken Math 30? Yes, and you have to be in radian mode a lot in Math 30. Yeah, I think you have to go back and forth a little bit, right? But certainly sometimes in radian mode. In physics class, Physics 20 and Physics 30, all through Physics 20 and 30, we will always want to be in degree mode. Now, because some of you are going back and forth between math class and physics class, we want to, every day we do a calculation involving angles, we want to do a little test. The first time. We don't need to do it every time we do a calculation, but the first time we do a calculation that day involving angles, we want to do a little test. And here's the test. Just hit sine 90. Sine 90 should equal 1. If it equals 0.899, you're in the wrong mode. You're in radian mode. Those of you who got 0.899 are going to need to click on mode, and then you're going to need to look at this where it says, well, you would have radian highlighted rather than degree. I can scroll down and I can click on enter by radian, and that changes me to radian mode. I don't want to be in radian mode, but you're going to do that. Scroll down here, go over to degree, click on that so that you're in degree mode. Does that make sense? Then we're just going to press clear. If I switch the mode, I'm just going to hit sine 90 again just to make sure that I switched it correctly. So, I haven't asked you to do this until today. Why? Well, because we haven't done any calculations involving angles until today. And if you're in the wrong mode, it doesn't affect anything that we've done so far. It doesn't affect anything that we do other than calculations involving angles. But going forward, we're going to have some angle problems, so it's going to matter. Don't do this. If we do 30 problems in a day involving angles, don't do this check 30 times. Do it once. Okay, if you're in degree mode the first time, you're in degree mode the rest of the time. Okay, so now here's how you calculate 10 cos 30. We're just literally going to say 10 cosine, whoops, not 1, but 10 cosine 30. Now, it automatically assumes the bracket for you, so you can finish off that bracket if you want, but you don't even have to. It will, the TID3 or TID4 will assume that final bracket for you. If I press enter, it's going to give you 8.66025. So, how much of this first one was x component? 10. How much of the second one is x component? 0. How much of that third one, 10 meters, is x component? 8.66025 is x component. Now, right now you're thinking like, oh, this is more like math than physics. You know what it is, actually, right now. This is more like math. This is not, like what we're doing right now is not the end. This is a tool that I'm teaching you or reminding you of that you've already learned in math class that will get us to what we're looking to solve for later on. So just bear with it until we're strong enough in the trig to move on to the actual physics part of it. Okay, how do we find the y component of that? We've got theta, right? We've got hypotenuse. We're looking for which side is y? Which side would y be? It's not hypotenuse. Well, it isn't adjacent because x was adjacent, right? Which side would it be, Xander? It would be opposite. Yeah. So which trig function would we use given theta, hypotenuse, and opposite? Theta, hypotenuse, and opposite would be which one? Yep. It would be sine theta is equal to opposite or hypotenuse. Opposite is the y-axis. Hypotenuse is 10. So we'd say y is equal to 10 sine 30 degrees, and that ends up being equal to 5.0 meters if you did that on your calculator. So how much of that 10 meters is x? 8.66025. How much of that 10 meters is the y component? 5.0 meters. Is that good? Yeah, anybody see another way that we could have found that y component? Yeah, Kevin? We could have done the Pythagorean theorem. Yeah, or we could have done tan, because we already have the x, right? Now, I would recommend against doing the Pythagorean theorem or tan, even though they're correct. I would recommend against it, because if you use those, you better make sure that x was correct. If you've made a mistake on x, then y is also going to be wrong if you do the Pythagorean theorem or tan. Does that make sense? Now, in the end, like, you do it right, you're good to go. But if we always go sine and cos, then we can get one wrong and still get the other one right. All right, let's try this one. 7 meters. What side of the triangle would that be? That's the hypotenuse, because it's the longest side, right? X component, what side is that? Here's my angle. The x component is touching the angle. It's not the hypotenuse, so it's got to be the, read, what would that be? Good, that would be the adjacent side. And the other one would be the other one, of course, would be the opposite side, right? The one that's not touching the angle at all. Let's say we're looking for the x component here. X component is adjacent. We already have hypotenuse. Adjacent hypotenuse theta. Then adjacent hypotenuse and theta goes with which trig function? Adjacent hypotenuse and theta. Cosine, yeah. Let's say cosine 50 degrees is equal to adjacent, which is x, over the hypotenuse, which is 7. Now, we don't need to do that little check on our calculator. We've already done that today. We know we're in degree mode. So I'm just going to hit 7 cosine 50 degrees. And I get an angle of, I get a value of 4.4995. So how much of that 7 meters is x component? 4.9995. Is that right? Almost. Almost. Yeah, actually, I'm not going to go sig figs here, because this is almost always going to be part of a bigger question. So this will not likely be a final answer for anything, right? We'd use that for something else. What is it that I'm missing there? Why negative 4.995? It's to the left, yeah. Yeah, if we assume right is positive, which we normally do, then left will be negative. Negative 4.9995. Okay, what about the opposite side? Let's not use the one that we just found, even though we could, right? Let's not use that. So if we're looking for opposite, we're given theta, we're given the hypotenuse. Which trig function goes with that? Opposite, hypotenuse, and theta. Opposite, hypotenuse, and theta. Tegan, which one would that be? Opposite, hypotenuse, and theta. Yes. So let's say sine 50 degrees is equal to opposite over hypotenuse. Let's say 7 sine 50 is equal to 5.3623. Is that positive? Yes, it is, because it's to the right. All right. How about this one? The angle, by the way, should be right here, right? It's not labeled very well, but it should be right there. This would be x. This would be y. Which side of the triangle is the 5? That's the hypotenuse, right? Marcello, which side of the triangle is the x? Yes. It's the first time x has been opposite for us, right? Usually x has been adjacent, but this time it is the opposite. Good. And which side of the triangle is the y component there, Brent? Yeah, that would be the adjacent. Good. Okay, if we're looking for the opposite side, looking for x, the opposite side, given the hypotenuse and given the angle, opposite hypotenuse and theta, which trig function is that? Opposite hypotenuse and theta, which trig function is it? Right. So I'm going to say this time, for the first time, sine 35 degrees is equal to x, which is opposite over the hypotenuse. What we usually find is that x is cos, but not always. See, sometimes it's y, like it is in this one. Okay, let's figure this out. Let's say 5 times sine 35 gives us a value of 2.8679. Is that right? Yes, who said that? Good. We're going to make that negative because, how come? How come you said that? Good, because it's to the left. Which side of the triangle is the y component? It isn't opposite. Sorry, it isn't hypotenuse. It isn't opposite, so it must be adjacent, right? Which trig function goes with adjacent, hypotenuse, and theta? Corey? Adjacent, hypotenuse, and theta? Sine, yes, good. So we're going to say sine, adjacent hypotenuse and theta is cosine, right? I made the same mistake as you did. Cosine 35 degrees is equal to adjacent over hypotenuse. 5 times cosine 35 is 4.0958. Yep. Is that right? Is that right? Aaron, is that right? Yep. Xander? Yeah, it's going to be negative. I mean, the number's right. Really close, right? But Xander, why should it be negative? Because the y component is down. We don't care about the x component right now. We're just dealing with the y component, right? X component to the left, I don't care now. That's done. The y component is down, so we're going to make that negative. That's why it's so important to draw the little arrows on the end of these vector diagrams, is so that you can see whether it's right, left, up, down, positive, negative, whatever. One last one, and then we'll wrap it up for you guys here. This one would be x, right? This one would be y. This 20 meters, that's the longest side. So Sam, what side would that be? Yes, good. Can't spell hypotenuse for some reason. Hypotenuse is hard to spell, actually, but I was just going to put the first 3 letters. I couldn't even get past the first letter there. H-Y-P, not H-P. Okay, that's a steak sauce, not a side of a triangle. H-Y-P. The x side of the triangle, the x side, Aiden, which side of the triangle is the x side here? The one that's, it's not touching the angle, right? It's the opposite side, right? So we're going to label that as opposite. Again, you get really good at this. You're not necessarily going to have to label them. You're just going to have it in your head. Here, the y component would be, Andrew, the y component is the adjacent side. Good. So let's say we're looking for the x component here, the opposite side, given the hypotenuse, given the angle. Okay, given hypotenuse, given theta, looking for opposite, which trig function am I going to use? Opposite, hypotenuse, and theta. Good. We're going to say sine 60 degrees is equal to opposite over hypotenuse. What does that work out to be? 20 times sine 60 gives me 17.3205. So how much of that 20 meters is x? Look, if it was this question, right, how much of this 10 meters is x? Easy, right? 10 meters. All of it's x. But if it's this one, how much of that 20 meters is x? 17.3205 is x. And the y component, well, at this point, you know the y component is going to be cosine for this particular one. Opposite over hypotenuse, and that works out to be, if we did that on our calculator, 10 meters. Okay? Okay. Let me just tell you one little thing here. I'm not going to write anything else down today, but let me just tell you one little thing, and this will carry through to next week as we start doing more with this little tool that we've just learned here. When we see one of these angles that's like 50 degrees or 35 or 60 degrees, we're going to call that a funny angle. 0 or 90, those are fine. We're fine with those. But if it's not 0 or 90, we're going to call it a funny angle. Okay? And then starting next week, every time you see one of these funny angles, every time you see one of these non-zero or non-90 degree angles, you're going to repeat after me. Okay? 5 words. I, repeat after me. I don't like funny angles. I don't like funny angles. No, that was pathetic. I don't like funny angles. Okay, so what are we going to do with the funny angles? We're going to turn it into X and Y. Listen, we're fine with this, right? And we're fine with this one right here. So let's turn these 50-degree angles, these funny angles, into this and this. Just X and just Y. That make sense?